Yeah, so today we are going to work with raster data. This is well, we have been teaching this course for a number of years already, but this is the first time we are covering raster. And that was a demand from the students, and it made sense because so far we have only worked with vector data. In the world of GIS, it's also very often we need to work with raster, so it was kind of missing from this course. And this is the first year we have this, so it may not be as polished as the rest of the lessons because it's the first time we are teaching it. But anyway, yeah, we will cover this today. So a couple of things about doing raster data analysis in Python. Yeah, so we all have studied GIS, so we know what's the difference between vector data and raster. One of the things, well, this lesson might feel a bit complex, a bit complicated, and the reason is that mathematically, raster data is a bit more complex than vector data. So we are working with these often huge matrices of numbers, values. So working with them is a bit analytically more demanding and should have a good understanding of how raster data works, and then you can work with the values in the matrix. So that's why it might seem a bit more complicated, but once you get to know things and if you have a good understanding of how raster data works, then it starts to get easier. But this whole course, a big part of this course was to motivate you to use also programming for doing GIS, and hopefully you're motivated enough. Another motivation for you is probably working with raster data. Raster data can be quite heavy, depending, of course, on what data you're working with and how large it is. It can be quite heavy, and it can become quite annoying if you're working with it in software and you're importing a large raster. It can get quite annoying. So using Python or any programming language for working with raster data is particularly helpful. Another thing is that, well, depending on what you're doing, very often you end up with a number of raster layers that you cannot combine, or it doesn't make sense to combine them. So you have to repeat analysis. And again, unless there is some plugin I'm not aware of, most GIS software do not allow you to do this like repeated action analysis on raster data. So in vector, you can have just one vector data set with many rows, so you can run a calculation that runs on all the rows. But with raster, there are separate files, unless you write some batch process or automate your work with programming. It's a bit tricky to work with them. Yeah, so there are a number of libraries that we will work with today. So they are very interconnected. So we are using them all kind of at the same time for doing different things. So the Rio X-array, Rasterio, and X-array, so they're all related, very dependent libraries. So you will see how it works. So the learning goals for today, we will start with the basics. Of course, we'll learn how to import raster data and do a bit of exploration to see if the raster data is single band, multi-band, and do a number of basic processing, some basic processing on the data. For that, we will use the Rio X-array and Rasterio. We will learn how to merge multiple raster files together and create this kind of mosaic, which is something we might need sometimes. Clipping raster using, for example, a polygon is another useful operation we often need to do with raster data. We will perform raster classification, and we will do some terrain analysis. We will calculate the slope and elevation models. And we will do some raster algebra or raster calculations, so doing calculation with multiple raster data sets. So that's the agenda for today. And we will start with exploring raster data. I've already pulled the changes from GitHub. If you haven't done it yet, please do now. But let's first take a quick look at raster data. So just as a quick reminder of what raster data is. Raster data consists of rows and columns of cells or pixels, with each cell representing a single value. this type of data is often thought of as an image. So very often when we think of raster, we think just an image, like we are used to working with PNG or TIFF files. That is true, but it doesn't have to be a picture. Also, raster datasets can be stored in various formats. So they can be also stored like as text files. So as I say, it's a matrix. Showing it as an image is just a representation of the matrix, one possible representation. Sometimes you might also get it as text files or binary large objects. So, but yeah, today we will work with raster image files, which is the most common. Yeah, so this is the structure of a typical raster image file. So it's made of pixels, and each pixel has a value, and then what this value means is basically coming from the metadata. So it can represent a land type, it can present the elevation at that point, or the temperature. So yeah. So this is a useful data format if you're working with a phenomenon that is continuous in nature. So very often we get data sets about temperature that come in raster format, or land use data sometimes. Elevation models are very often in raster format. So there are two primary ways of working with raster data. There are two types of raster, well, in terms of the number of bands. So we have single band raster files. So we just have, so it's like two-dimensional. You just have a single value attached to a pixel. Then you might have multi-band raster files. So it's as if you have multiple pictures, like different layers of images on top of each other, stacked on top of each other. This is very common, for example, with satellite imagery, that they come in like different bands, different wavelengths. So if you're working with anything related to remote sensing, this is very relevant. A key characteristic of any raster data is its resolution, and this is something we will work with briefly today. Resolution refers to the ground distance of each cell. So if you have a cell, 1 pixel, what area does it represent on the ground in the real world? You might get your raster data in different formats. TIFF or GeoTIFF is the most common, maybe, but you might also get raster as other image formats like JPEG or GIF or bitmap or PNG. And as I said, it can come also as text, like ASCII grids are also quite common, especially for larger data sets. Yeah, so as I said, we will be working with these three libraries that are very connected. So one thing that they have in common is this Rasterio. So Rasterio is one of the main libraries for working with raster files in Python environment. So this is a good library to learn, but we won't explicitly use Rasterio today. Instead, we will use these three other libraries, which are more modern, but under the hood, they use Rasterio. So Rasterio is a big library that is built on top of GDAL, this geospatial data abstraction library, which is this huge C-based library for doing a lot of GIS tasks. So many libraries in GIS world are built upon GDAL. So these are the libraries we will work with. So we'll start our lesson by importing the raster data, and then we do some visualization and a number of calculations. So the data sets that we will be working with, we work with two data sets, two raster data. So the first one is a satellite image. This is Sentinel. I have a typo there, but yeah, Sentinel data from Nuuksio National Park in Finland. So I've gotten the data from the Copernicus data center, data space, so it's open data. Of course, you have to sign up, then you can download the data, but the data is open, so you can get it yourself. And then we also will work with elevation model data, which we have gotten from National Land Survey of Finland. So those are the data sets that we will be working with. So let's jump to our CSC notebook or NOPE environment and start with Raster Explorer. So one thing about raster, we will see how this works in NOPE environment, but raster processing can be quite heavy, very demanding for a computer. So we have made the raster files a bit smaller here, so the area they cover, they're not very big. But if you work with large areas, it can be quite demanding. So it takes a lot of like CPU and memory from your computer. So here, because we are working on NOPE, we don't have so much control on the power of the machine that we are running on. So at some point, sometimes we might have an error like running out of memory or something. But this would work more smoothly if you're doing it locally on a more powerful computer. But this is now CSC, so we don't have so much control over that, but let's hope everything goes smoothly. This is also relevant when you're doing your exercise. We have tested it should work fine because we have made files smaller, but this is an issue that might happen with raster data running out of memory or the kernel breaking because of that. So yeah, so let's start by loading our single band raster data. The data is the DEM, the digital elevation model that we'll start with. If you have worked with National Land Survey data, the digital elevation data coming from National Land Survey, you know that it comes in tiles. As I said, raster can be huge, so it just doesn't work. You cannot have one raster of the whole elevation model of Finland. It just becomes enormous. So it comes in tiles and they're coded. So if in the metadata you can see where this is from. But this is now from Nuxio area. So this is what we will be working with. Let's just start by loading the data, and we are doing that with the library called RioXarray. So first we provide the path to our TIFF file, which is stored under data directory. The next step is, of course, to load the elevation model. So I will name it elevation raster. Then I will use RioXarray. It has a function called openRasterio. As you can guess from the name, this function is coming directly from Rasterio library, which is the mother library of this newer raster libraries that we will be working with this week. So then I will provide the path to my data file, which is stored already in raster file. And let's run this. So now the data is loaded. Let's start by exploring our data a bit. So let's print and see what we have under elevation raster. So if you use print and then the name of the raster file, what it will give you is some brief metadata of the raster. So it gives you some quick information about what you have. So as you can see, it's a single band raster. You can see the dimensions. So you have 3000 by 3000 pixels, and the size of the file is 36 megabytes. And the values are float 32-bit. The band number is, of course, a number. It's an integer. And then you have X and Y coordinates, which are float 64-bit, and a number of other useful information. So yeah, by printing, you can quickly see some metadata, some facts about your raster file. So let's also check type. This is something we have often done. So you can see it has been loaded as a data array. So this is what makes, as I said, it's a matrix. So what we are doing essentially when we are working with raster file, we are working with a matrix. So that's why it's loaded as a data array. So it's an array of numbers that we will be working with today. And this can get quite complex depending on how your raster is structured. Yeah, so that's the data type we are working with. Another useful information for us is, of course, the coordinate system that the raster file comes in. So let's check the coordinate system of our elevation raster. And for that, you can just access rio.crs. And this should give you the coordinate system. So this is coming in 3067, a familiar coordinate system for those of us who work in Finland. So let's also see how we can quickly plot our raster. So again, elevation raster, as you might guess, you can just use the dot plot attribute to map your raster file. So this is a very quick representation of the raster. You notice probably it took like a second or two compared to a vector. Of course, it depends on the vector data, but generally speaking, it's a bit heavier to work with raster. But yeah, using the same method .plot that we are familiar with, we can quickly create a plot. Again, this is using matplotlib under the hood. So everything we learned on week 5, when we were working with visualization applies here too. So if you want to customize your map, you can use the same things that we learned in the previous weeks. So NumPy is a library that we have not explicitly worked with, but you have heard its name many times during these 2 courses because it's a very powerful data science mathematics library, and it's super useful when it comes to working with arrays, like we are working with now in this lesson, working with raster. Yeah, so now we are going to use the NumPy library and print some basic raster statistics. Yeah, so we have already the code typed in, so we don't have to type anything. So we are printing a number of f strings, and from that, in the first one, for example, from the elevation raster, we are getting the minimum, and then we are also getting the max, the average, the median, and the standard deviation of our pixel values. So let's just run this. It quickly gives us some idea about the values we have in our pixel. So this is a digital elevation model, and it's coming in, it's in meters. So you can see the minimum altitude we have in our data is -19 meters, and the highest point in this area in Uxia from this tile is +35 meters. The average is 1 meter, so quite flat, pretty much on the sea level. And the median value is 0.32, and the standard deviation is 3 meters, so not a bit of variation, but not so much. So we can quickly get some statistics from our raster data using NumPy. These were just a few examples of things we can calculate easily. So this is something, next thing is loading data from WMS service. This is something we will not cover now, but we just quickly look at it. Well, similar to vector data, we often got our data just by downloading from somewhere, some source, and then working with it. But we also saw that you can get your vector data, for example, through WFS, so World Feature Service. So a similar service exists for working with raster data, and that's called WMS, which is short for Web Map Service, and it is defined as part of the Open Geospatial Consortium, this protocol that governs the world of GIS. Yeah, so there are a number of services, like very often like organizations share their raster as files you can download, but also as a WMS. For example, in Helsinki, this data set that we will be working with, not working with, but just getting through WMS and taking a quick look at, is coming from Helsinki Kantakartta dataset. So yeah, so the Helsinki Services has provided this base map that we will load and look at. We are using a library called OSLib for importing this, again, to see how you can construct your URL for WMS, very similar to what we did with WFS. You should check the metadata of the service provider to see how you can construct a URL. And very often a good starting point is, for example, QGIS. If you want to browse the data and see how it works, you can take it, you can connect to the WMS server in QGIS and then see what layers are available. So here I have already checked what layers are available, and this is what we are getting, this Kantakartta. So yeah, so we don't go through this, but just an example of WMS. I've gotten the URL from the metadata of the service provider, and the construction is pretty similar to WFS. Let's just run this and get our output. So I have also added a line of code which gives you a list of the layers that are available in the data. So I've just put a for loop so it doesn't go through all of them, because there are tens of layers available in this service. So yeah, so using this code, you can get a list of the services, the layers that are available in your data. But yeah, to just quickly show you, we just use WMS to get this image. So it's a raster data. But what we will be working with today is datasets that we have just downloaded directly from the service provider. And now we are going to move on to a multi-band raster data, and it is coming from Sentinel. So it's a satellite image from Nuxio area. Yeah, so let's continue and import the data. So importing is quite similar. We are importing a number of libraries that we will be working with later on. But for reading the data, it's the same. So we are using RioXArray to load the data. This is the path to the file. It's also stored under data. And it's a smaller version. The original tile was a bit larger, so we have made it smaller so CSC NOPE can handle it. I'm loading the data in a similar way. Let's just run this code. So the data should be now loaded. Next thing I'm doing is plotting my raster. And as you can see now, there's a difference. So last time when we ran the .plot on our single band raster, we could just quickly produce the map. So we just visualize the raster as a map. But when you do it on a multi-band raster, what you get is a plot, is a bar plot. Yeah, so what this is basically showing you is the frequency of different pixel values. So if you have a multi-band raster and if you just use .plot, it's not going to give you a map because there are many bands, so the library doesn't know which band you want to visualize. Later on, we will see how we can single out one band and then visualize it. But if you just do it like this, it will just look at all the values you have in the array, all the pixel values. It has probably normalized the values, and then you see the pixels. So this is like 3.5 times 10 to the power of 6, so hundreds of thousands of pixels with that value. So yeah, so .plot works differently if you're working with a multi-band raster. So let's print the metadata of our raster file, and we saw how we can do that. So we just use print. Then I will just copy the name of the raster file so I don't have to type it, but it's Nuxio Sentinel. So similar to single band raster, if you print the raster, you will get some metadata. This time you can see the information is of course different. It's a different file. The band number is 12. So this is a multi-band raster with 12 bands. So you have basically 12 images stacked on top of each other. The size is 32 megabytes, and you have almost 8 million values that are in float. They're float, so they have decimals, and yeah, and you have coordinates. So it's a geotiff. So yeah, so we saw the metadata. But in order to make sense of the bands, just by looking at the raster data, you cannot tell what it is unless you're super experienced and you know it so well. Generally, what you do again, you just check the metadata. So when I got the data from the Copernicus platform, there was also metadata explaining what each band is representing. So this is a standard for that satellite that produces that image. So in band 1, we have coastal aerosols. In band 2, we have the blue wavelength, and band 3 is green, band 4 is red. So depending on what you want to do, you choose the band that you want to work with. For example, something that you will be working on in your exercise is to calculate NDVI. And for those of you who have studied remote sensing, you know that for calculating NDVI, you're interested in this near infrared wavelength. So depending on what you need, you just extract the band that is useful for you. So now we'll start by just seeing how you can single out one band that you're interested in. So the band that I'm interested in is the red band. So I want to access that one. So from metadata, I know that the band, red band is stored as band number 4. That information I'm going to use to extract the band of interest. So I'm going to store it under a new name called red band. Then from the raster file, nuxio_sentinel, using .cell, this is short for select, and then you provide the number of your band. So as we saw from the table above, band 4 was the red band. So now you just loaded band number 4 and stored it under red band. So it is basically another raster. So you just extracted one of the bands of your raster. So yeah, so now it's it's like a separate raster. So now if you tried red band.plot, now it should work. So now that you singled out that one band, it's like a normal raster. So when you use .plot, then you can see what it looks like. If you want to do it more quickly, just on the go without storing your band into another variable, you can also do that at the same time, of course. So let's take a quick look at band number 2, which is the blue wavelength. So from the same raster which I've already loaded, I use cell to load band number 2 this time. And of course, I can just quickly plot it. So we can, of course, do everything in just one line of code if you do not need to store it under a new variable. Yeah, so next thing we want to do is to create a composite raster. So if you get your raster in normal light, like normal wavelength, so it's a combination of R, G, and B, red, blue, and green. So what we are going to do is to create that composite raster that includes red, green, and blue. So we are extracting these 3 bands from our raster, and then we are creating that new raster that includes all 3 of them. So again, from that table above, I know that the red band is number 4, green is number 3, and blue is number 2. So I'm extracting those. So part of the code is typed in already. So the first 3 lines is just extracting the layers, the bands that we are interested in, 4, 3, and number 2. So the next thing I'm going to do, I'm going to stack them on top of each other. So for NumPy provides you with a function that does that. So what you're basically doing, you're creating this multidimensional matrix. So you have red, green, and blue. And for that, there is a library. So I'm going to store the output as RGB_image. And from NumPy, which I've already loaded as MP, I'm accessing that library, that function that is called dstack. So it's dstack, I guess, probably short for data stack. And here you provide what you want to just stack on top of each other in your raster. So I want to use the red, green, and blue values. So those we have already loaded. We just put the name. So red_band dot values, green_band dot values, and blue_band dot values. So next thing I'm going to do is to normalize my values. So we already looked at the statistics of our raster, so it comes in a wide range of values as they're measured by the satellite. But for our plotting to work, like Matplotlib works with normalized values. So if they're within the range 0 to 1, then Matplotlib can visualize them better. So that's what we are going to do. So we have loaded our values. Now we want to normalize them to the range 0 and 1. So this is just doing some simple mathematics. So I'm going to rewrite the same variable. So RGB image. And then I'm going to just divide the pixel values by the maximum value I have in my pixels, so that the output would be normalized. So I will use npmax RGB_image. So what I'm doing here is just normalizing my values to 0 to 1, so the data becomes a bit simpler and it works well for plotting. And I'm normalizing it by just dividing each pixel value to the maximum value I have in the whole raster. So the rest is just plotting. So I'm just using .plot, but to make sure it works better in here, I've added a few extra things, but just simply using .plot. Yeah, so now we've produced a composite raster file combining the information we had from red, green, and blue band. So this is a bit closer to what natural, like how you would see it with your eyes. So this was a very simple, basic overview of how you can import single band and raster and multi-band raster. In the second part of the lesson, we are going to continue doing a bit more processing on the raster. So let's move on to the next notebook. So does it make sense so far? Yeah, very simple things. Now things get a bit more interesting in the second part. So let's open the next notebook, raster processing. So now we want to do a bit more advanced things. So first thing we start with is creating a raster mosaic. As I said, raster files can be quite large. So very often the service providers provide raster files as separate tiles. So in Finland, if you're getting, for example, the digital elevation model from the National Land Survey, it comes in tiles, so pieces. So if you want to combine them, put them together, because the files becomes smaller. But if you want to work on an area as whole, then you might need to create this mosaic of your tiles. So you put them together to have one raster, then you can run your analysis on that. And this is what we are going to do. In the first part of the lesson, we just worked with one of these. Now we are going to work with 4 of them. So these elevation models are coming from center of Helsinki. So if you look at the National Land Survey, you will see that the center of Helsinki, the peninsula area, is divided between 4 tiles. That's how they have divided the data. So if I want to have the whole center of Helsinki, I have to put these 4 mosaics together. And now we will visualize things so you will see what I'm talking about. Yeah, so let's just load our data. This is all familiar. I'm opening the raster file using Rasterio through RioXarray, and then reprojecting it at the same time. And the rest is just plotting what we have seen with Matplotlib before. So let's just load and see what we have. So we are doing this now for 4 files at the same time, so it's taking a little bit longer. Yeah. So these are the 4 tiles I'm talking about. So these are the elevation models from center of Helsinki. So there are 4 separate tiles, as you can see here, and what we are going to do next is to put them together so it becomes one bigger raster that we can use for our analysis. So as I said, these are familiar. So this is Matplotlib. So if you want to customize the visualization, you can just easily do that as we have learned before. So now we want to move on to creating our raster mosaic. And through this library that we are working with, this RioX-array, there's a function that does that easily for us. So it's called merge_arrays. So that's the library we are going to work with. As you can imagine, it is important that the raster files you're putting together are compatible. And that basically means that they align well, because you're working with pixels. These are images. So they should be aligning. So they should be the same in shape, the pixels. They should be the same in size, and they should be aligning with each other. So when you put them together, it works. In this case, it's not a problem because these are 4 tiles of the same data provided by the same agency, National Land Survey. So I'm not worried about them matching because it's coming from the same place and I know they will be aligned well. But if you have concerns, if you have gotten your data from somewhere and you're not sure if the alignment works well, of course you can explore it yourself. But there's also a function provided by this same library called align that can kind of automatically take care of things. It doesn't always work so well, but as a starting point, it might be good to test that. So for example, in this example we have here, we align raster 1 and 2 and raster 3 and 4 to make sure that they are aligned. So it just readjusts the pixels and how their layout so the merge would work successfully. But as I said, in our case, it's coming from the same source and I'm not worried about their alignment. It should work fine. So let's start with doing the merge. So from RioX-array, .merge, so a submodule of that library, I will import a function called merge arrays. Then I'm going to pick a name for my output mosaic. I'm going to call it mosaic merged. And then what I need to do is to use the library the function I just imported, which was merge arrays. The next thing I'm going to provide, what I need to provide is a list of what I want to merge. So it's a list of those raster files. So we have imported the rasters as raster 1, 2, 3, as you can see up here. So I will provide a list of my rasters. So raster 1, raster 2, raster 3, and raster 4. So it can be as many as needed. You can just provide a list. We are not going to use this, but just as an example, if you need to export this, if you need to save this TIFF file, you can just, there's a function for saving the raster. So for example, mosaic_merge, which is the output of our merge, I can just use Rio to raster to export it as a file, as a TIFF file. So if you needed to save this on your disk, you can just use it. And what you need to provide is the name of the file or the path to the file's output. So I'm going to just comment it out for now because I don't need to save it to the disk. I want to save the space. But yeah, there's a function for exporting your raster file. But what I want to do is to plot it. So I will use mosaic_merged. and just use the dot plot to get it to my screen. I have a typo here. It's a bit heavy process, so it took like 10 seconds to run it, but the output is just one raster. So we had these 4 tiles that we visualized already as subplots. We put them together, and it's a bit hard to say, but maybe you guess already the shape of the center of Helsinki. So it was 4 tiles, so it was like divided between several raster files. So now we combine them, and now we have a mosaic raster covering the whole Helsinki center of area. Next thing we are going to do is to use this raster and get a polygon of a single neighborhood from Helsinki. So we are going to work with Compi. We get the polygon of the Compi from OpenStreetMap, or actually we are getting it from WFS. So we get the polygon, or you might have it just locally on your disk. We are using that polygon to clip the data. So as you can imagine, Compi is somewhere here. It would have fallen between several raster files. So if I was doing it with separate raster files, it would have been tricky. But now it's just one raster, so it's easy. So I'm going to just, from WFS, I'm going to load the neighborhoods in like the postal areas in Helsinki area. So let's just do that. WFS we have used several times already before. And then we just print the dot head. If you need to save it as a file, as a geo package, for example, you can of course do it, but for now I'm just commenting it out. So this is a list of the postal areas in Helsinki region. So from this I'm going to extract the area that I'm interested in. So in this case I want to go with Compi. So if I know the, of course you can go with name or whatever, but I'm going to use postal area, and I know the postal code of Compi. So I can use that information to get the polygon of Compi, which I can then use for clipping. So I know that the postal area that I'm interested in is 0000. So I'm going to, well, this is a GeoPandas, a geodata frame, so we can just easily get the row that we are interested in. So from post area, I will get the row that corresponds with this postal code. So that's the first thing I'm doing, getting my polygon. And this is how you, so the next thing I want to do is the coordinate system. As I said many times already during this course, coordinate system is important, and you should make sure whenever you are working with multiple layers, they're matching. So now you got your, so we don't know if the postal area and the raster are in the same coordinate system. Just to be sure, I will take my Compi polygon, which I just selected from a geodata frame, to the same coordinate system as my raster. So I will use Compi.2CRS, and I will use the coordinate system of my mosaic raster. So this is the mosaic merged raster that I used, and we already saw you can access the coordinate system using rio.crs. And once we do this, there's also a plot to see the polygon that we are going to use for our clipping. I had a typo. Yeah, so this is the polygon of the Compi postal area. I'm going to use this polygon in the next step to clip my raster. Because I'm paranoid, I want to again make sure that the coordinate systems are matching. So I have this assertion that we have seen many times. Because we are putting the 2 layers on top of each other, so it's important that they are in the same coordinate system. And if not, you will get an error here, assertion error, that CRS doesn't match. Then it's, once you're sure they're in the same coordinate system, I'm going to clip my raster, and I'm going to name it clipped mosaic. And there is a function that can take care of this clipping. So mosaic underscore merged. There is an attribute called rio.clip. So the next thing I will have to provide is the geometry of the polygon that I want to use for clipping. So I will access from my compy data the geometry column. So we already converted our coordinate system, so we know they are in the same coordinate system. But this function allows you to take your polygon to the same coordinate system as your raster. So we did this already because it's nice to be in control and to make sure everything is fine. But you can also provide the coordinate system. So it can take your vector data to the same coordinate system as your raster. So you can just provide the CRS. So I'm going to just use compy.crs. But this is not necessary here because we have already taken them to the same coordinate system. This line of code is commented out. So if you want to save it as your clipped mosaic compy, for instance, you can just do it using rio.toRaster. We are not going to do that. Instead, we will quickly visualize our output. So clipped underscore mosaic dot plot. So now you can see that this is your output. So the area within compy neighborhood, compy postal area is white, and then you have blue pixels out of the boundary. So we have done the clip. You can see something has happened to the raster. But what you're seeing here is that the areas that are outside the polygon are just null values. So they're missing values. Here, automatically, Matplotlib has visualized them as blue. So to make our visualization better, we are going to get rid of, we are going to mask out those areas which are null now. So when we did the clipping, these blue areas which are null, probably they were assigned with some random value, -999 or something like that. So that's why we have this dark blue area. So this is a very important thing when working with raster data, handling null values. So let's see how that works, because this will affect your visualization, of course, when you have null values. And later we are doing data classification. If you have null values, this is going to be problematic. So what we are going to do now is to mask the no data values. Yeah, so I will get my no data value, probably so -999, something like that. But there is an automatic way of accessing that. So I'm going to, from no data, I will store it in no data value. From clipped underscore mosaic, which is my raster file after clipping. Rio allows us to get the no data like this. So rio.nodata. So now that I know through this function what are the no data values, I'm going to use that information to mask them out from my raster. And for that, there is a method in NumPy that is useful. So let's write the code, and then we will. Well, let's look at it first. So from NumPy, there is a function called where. So the NumPy where function is a conditional function that allows you to select elements from an array based on a condition. So what you do is a bit similar to what we have in pandas, just differently called. So from where you can provide a condition. In this case, condition is the no data values. So I'm just telling NumPy to mask out the no data value, or just exclude the values which are marked as no data value. So you can put any condition. You can say, okay, keep all the values that are bigger than 10. So you can put any condition. So NumPy where function is very useful when working with rasters. So I'm going to rewrite the clipped raster. I will put a condition. So from clipped raster dot where sorry, clip mosaic. Yes, sorry. Yeah. So from clip mosaic, I'm applying this condition, and the condition is that the clipped mosaic should not equal with the values I have identified as no data value. So I have identified the no data values here, no data value. So this can be any, as I said, it can be any condition. You can just keep everything that is bigger than 5, bigger than whatever. Here it's unequal to no data value. So this is one way of masking the values that I don't want to be included in my raster. So then I'm going to plot it out to make sure that the output, it has worked. So I will just use .plot. So now you can see the output immediately looks better because it got rid of those values, this arbitrary values. So the missing values were -9999. So I left them out of my raster. Now that I visualize, Matplotlib can do a better job because values are within a reasonable range. So there is no -999. So it's ranging from -30 to 30. That's the elevation of this COMPI area. So it ranges between those values, and it automatically does some classification for you, so you see the values visualized. So yeah, so when you're visualizing, if it looks weird, you probably, well, one of the reasons can be that you have no data values and they're affecting how things are visualized. So you can get rid of it using NumPy, where putting a condition to get rid of those values. So now I want to do reclassification. This is another useful thing we very often do with raster files. So you have a certain, well, we already saw classification, was it in week 4? It works, we need it sometimes with vector data, but with raster we use it quite a lot. You have values coming in a certain range in your original data set. You want to take it to a different range. For example, now we have the values from -30 to 30. That's in meters. Maybe you want to just tell whoever is using your map whether the place is lower than sea level, or higher than sea level. So this is an example of a case where you would need to do reclassification. So now we will see how we can do reclassification with raster files. Useful, well, from the plots you can guess what is the range of your value, something between -30 and 30. But to have better information, let's start by printing the minimum maximum values of your plot. So actually the lowest area is -2 meters all the way up to +32 almost. So this is the range of the values that we have. So this is pretty similar to what we did with week 4, the classification. So we have 2 ways. One way of doing a classification is, of course, manually. You can just define your classes saying that, okay, if it is minus, it's under sea level. Around, if it is around 0, -+1, it is flat or at sea level. So you can do it manually. The other option is to use some of the well-known classification methods, for example, natural breaks. And again, we can use that same library, MapClassify, that we learned in week 4. So these are the 2 options, and we're going to try both of them. Yeah, so we start with the first solution. So the first example where we are doing things manually. So the code is typed in. We don't need to type anything. Let's just go through the code and see what we have. We are importing the libraries that we need for our work. We have imported them before, but yeah, we are importing again. And yeah, so xarray, numpy, and matplotlib pyplot. Then I'm defining my bins of classification manually. So I'm just saying, well, the smallest value was -2, but anyway, I've just put -10. So that's like the lowest threshold. So from -10 to 10 is one class, 10 to 20 is another class, and 20 to infinite. Or you could have just put a big value. Here I've just used numpy's inf, but is infinite value. So anything bigger than 20 meters would be in my third class. So this is the classification. Of course, you can define it however you want. And then what is the new value you want to assign? So you define another list, and these are the new values. So I want to assign them to 1, 2, and 3. So if it is -10 to 10 is class 1. If it is 10 to 20 is class 2. More than 20 is class 3. So these are my new values. So this is how you can manually reclassify your raster. The next thing I'm going to do is to mask out the non-values. So when you were working on your exercise 4, I guess, you saw that probably some of you ran into a problem with non-values. So MapClassify is a good library, but one problem it has, it doesn't automatically identify the missing values. So even if you have marked them as non-value, still it might end up in your classification. So it can cause a bit of problem. So that's why we are going to get rid of the missing values here, or the non-values. Yeah, so I'm masking my raster using that similar function. So this time you're doing something different. You're checking if it is a missing value. So we have this sign that we haven't seen before. So you can write the logic however you want. Here I've used something different. So this is does anyone know what the sign is called? But anyway, what it does, it just negates what you have. So if the value here is none, is true, it's going to return false. So it just turns around the value, then it negates the value of the bit. So if it is a true or 1, it becomes 1, a 0. If it is 0, it becomes 1. So I'm just turning the logic around. So if the value is a missing value, this will return false. And then if it is a correct value, if it is not a missing value, then I'm just using the original raster value. If it is a missing value, then I mark it as a numpy none. So this is the logic here. So this is just turning around. So if it is false, it makes it true to make my condition work. But this is the actual, so this is the clipping part. So I got rid of things, missing values. The next thing I'm going to do is to apply the reclassification. And so this is the part that we are actually doing the classification. So I'm creating a new raster. I'm going to call it reclassified raster. From NumPy, there is a library that can, there is a function that does this reclassification, and it's called digitize. So what you need to provide is your raster, which is the masked raster. Then you will need to provide the bins that you have defined up here. The next thing is, it's an optional parameter, but it's right. It can be true or false. By default, it's false, and it tells you if a value is, for example, 10, where does 10 fall? Is it in the first category or the second? Because it's on the threshold of the two categories. By default, it puts them in the left one. But if you set right to true, then it will put them to the right bin. So yeah, so depending on how you want it to work, you can set something here or just exclude it. But if you exclude it by default, it will fall into the left bin if it is on the threshold of the two bins. So right is true. So once I'm doing my classification, again, I'm repeating what I had here. So I'm making sure there are no missing values in my output, because I want to visualize it and I don't want the same thing to happen. So I'm just basically repeating the same line of code here with this other, with the output raster. So now what you have done, this is a NumPy array. So when you're working with the values, this is no longer a raster. So it doesn't know it's a raster. To make it a raster, again, you have to reattach the original attributes of your raster. So what we are doing here, I'm converting this to an X-array data array. So what I have to do, well, this is what we have, the reclassified raster. I'm getting the dimensions of my raster. So these are the things that make a matrix a raster, as defined by this library. So I need the dimensions, so dims equals clip. So I'm getting the dimensions of my clipped raster, the original file, before I started doing these things. Then I need the coordinates, because it's not only about the pixel values. We also need the coordinates of where this pixel is located. So I'm just directly getting it from my original raster and other attributes. So if there are other attributes, I will just import them from my raster from the time before I made these changes. And then I'm creating my plot and specifying. So instead of putting 1, 2, 3, I'm just writing low, mid, high on my legend. So let's just run this, and you get the output. So you reclassified your values to 1, 2, 3. And just for the sake of visualization, I applied different names. So instead of, if I didn't provide this line of code, it would have just had 1, 2, 3 on my bar, on my legend. But instead I'm using set tick labels, and I'm providing low, mid, high to just make it more readable for whoever is using my map. So you can see areas which have low altitude, average altitude, and high altitude. Yeah, so this is an example of where you wouldn't change the legend. So let's skip that. So that was the manual way of applying the classification. Now we want to do it automatically, like kind of automatically using map classify. So you can use natural breaks. You can use all those algorithms that we learned about before. So what I'm doing is importing map classify this time. So for the map classify to work, I have to, well, we have a matrix, so it's multidimensional. But for map classify to work, I'm going to flatten it into like just one array, and then I go through the values. So we are flattening the values. So these are things that they are good to know. They might be a bit too much for today, and you don't need them for your exercise, but yeah, just going through a bit more advanced stuff for raster data analysis. So I'm flattening the raster, making it just one array that I can do my classification on. Again, I'm applying a mask, checking what values are marked as none. Then this is where so what I need, as you saw, we need those bins defined as a list. Last time we defined those bins manually. I just put -10, 10, 20, and then infinite. What you can do, you can get those bins from map classify. And this is something we have done before. So I can define natural breaks and apply map classify on my raster data that doesn't have none values. I already got the missing values, so it doesn't mess with the classification. It's natural breaks. It needs number of classes you want. I'm using 7 classes. You can try it for different values. And then what I need is these bins. And from natural breaks, you can access the bins like this. This is something we saw on week 4. And then the rest is the same. So the only difference was that instead of defining bins manually, I just used natural breaks in that library to get it. And then the rest is the same. So I'm providing the raster and the bins that were this time defined with these natural breaks. And then the rest is just visualizing. So let's just run this and see the output. yeah, so now we have 7 classes. You can see the values up to 7. And yeah, so we did the classification using natural breaks. So what it needs, that digitize function, is to, yeah, so it needs bins. Those bins can be defined manually if you know how to do that, or you can use map classify and a well-known classification algorithm like natural breaks to get those bins, and then it does the classification for you. Just be careful with missing values when you're working with this, so they don't fall into a class. This was a problem that some of you had in the exercise 4.
The reclassified raster, is it possible to access pixels that are in a certain class? If I only, in this example, wanted the ones that are class 5, I want to plot that separately with the raster.
Yeah, so what you can do is, like, when you're flattening it into a list, then you can just put a condition, and similar to what we had when we did the where. So with where, you can filter out the values that meet a certain condition. Yeah. So it's the same as when we filtered out the missing values, just put a different condition. Yeah, so next thing we want to do is the slope analysis. So this is not about how to calculate the slope. So this is not what we are covering in this course. This is just an example of how you can do raster calculations. So what we calculate here is not important as such, but rather how do we do these calculations on our raster. So you probably know that the slope analysis is one of the terrain analysis techniques that we sometimes use in GIS to just, well, as you can tell from the name, to see the slope of terrain at different areas. So from digital elevation model, you can calculate that. So yeah, so the data now, we are working with a different data set coming from the same source, National Land Survey of Finland, but it's coming from somewhere in Lapland. So it's one of these, it's a fell, like it's a hill in north of Finland, at least local people are familiar with. And yeah, so we are going to work with that and create the slope. So we are going to do these calculations, and this is how we calculate the slope. So this is not important. Like, it is important in this analysis, but this is not what we are learning. It can be anything. If you were working with temperature data, it could be a function converting temperature from Celsius to Fahrenheit. So the idea here is to see how we can do the calculation. So what we are going to do first, of course, is to import the raster file. So it's a different tile from the same provider. Let's plot it first to see what we have. Yeah, so this is the area. As you can see, this is the peak of the hill, Tunturi. And what we are going to do is to calculate the slope, how the angle of the slope changes in different areas, and visualize that. So again, the code is typed in. And this is just one example of how you can calculate things with raster. So what I'm going to do is to see how much the altitude is changing from pixel to pixel. I want to get the slope. I want to calculate the degree. So how do I know what is the distance? So what do I need to know? I need to know how the value changes from pixel A to pixel B, which are adjacent to each other. I know the altitude, so it's the difference of how the z values, the value of the pixel changes from this pixel to this pixel. The other thing I need to know is the distance. Then I can just use this equation to do the calculation. So I need the distance and the change in the z value. So how do I get the distance between pixels? Well, it's from the resolution. So from the resolution of my raster, I know that this pixel, for example, corresponds with 200-meter distance in real ground, on real ground. So that's what I'm doing. I'm getting the X resolution and Y resolution. So from your raster, which we already imported up here, did we run this? Yeah, we did. You can access the resolution. So with index 0, it gives you the resolution on X axis. with index 1, it gives you the resolution or the real distance on the ground, the size of pixel on the y coordinate, y axis. The next thing I'm calculating, I'm just trying to see, I'm calculating how the z value, the value of the pixel, is changing from this pixel to this pixel. So there's a function for that called differentiate. And with differentiate, you can provide the axis, so chord x or y. It calculates how your values of pixels, how your values of a raster are changing in x direction and y direction. So this gives me what I need here. So divided by resolution. Then the next thing, I'm taking it to power of 2 to get this equation. As I said, the formula doesn't matter here. And then the next thing I'm trying to do here is to transform this to degrees. So I'm just using some mathematics to take this to degrees. Again, this could be anything. It can be temperature conversion. I just tried to choose a geographical example. So now that we did the calculation, I'm going to plot it in the next step. Yeah. So one thing I did, once I did the calculations, I updated the attributes. So I changed the name of the name is one of the attributes of the raster. I'm changing it to slope, and then the units to degrees. And then the visualization looks nice. So once you convert the unit to degrees, it already has some understanding of what you're plotting here, and the plot becomes a bit nicer looking. So with just few steps, we did some simple math. You created a slope, and the visualization looks quite decent, even without making any further customization. So this is an example of how you can do some simple or complex mathematical calculation on a raster and get what you want. The next useful thing is raster to raster calculation. In old days in ArcGIS, I guess now they have changed the name. It used to be called map algebra. There used to be a tool called map algebra. In the newer ArcGIS, it's called, I guess, just raster calculation. So it's basically in what we did in the last example. We worked with only one raster. Then we did some calculations on the existing values. What we are doing now is that we have two or multiple rasters. We do some operation between them. So I can multiply this raster by this raster, for instance. So it just does some mathematics called calculations between raster values. So again, this is an example of something we are measuring that is irrelevant to what this is not something you need to learn. We are calculating a slope stability index. I just wanted to have an example of something that we can calculate based on what we did up here. So it doesn't matter what it does, but how it is calculated. So SSI is calculated like this. It's 1 divided by slope multiplied by elevation. So we want to calculate this. So it's just a simple mathematical calculation. We have these two raster files. We just multiply them by each other, and then one is divided by the result of this. So this is how we can do this map algebra. And last time I tried this actually on CSC Noppe, it couldn't handle this, but let's see how it goes. It was having a problem with the plotting part, so I'm going to just cut that part, put it in a different cell in case it crashes. So in this case, I'm reading the data. The slope we already have. So I'm just reading band 0. In this case, it's unnecessary because we only have one band. But this is just to show you that if you have multiple bands, of course, you can just provide the band number and access that band. In this case, we just have one band, so it's okay. So this is a condition that related to what you asked earlier. So if you have a DEM and you want to filter based on a certain value, you can just use where, put a condition bigger than 0. It filters out those pixels that are bigger than 0. So next thing I'm going to do is to calculate the SSI. And that's the only part of this equation. So this is what matters most. we have the equation, we want to do the calculation for raster. So the way to do it is very simple. So you provide the output. I'm just going to, the output raster will be called SSI. How do we do the calculation? Simply just copying what mathematical equation we have. So we can treat raster layers as just variables containing numbers, kind of. So slope times them. So I just basically copied what we have here. So SSI equals 1 divided by a slope times elevation. So simply like that, as simple as this, you can just do map algebra. So this could have been anything. You could just sum them up, you can do division, you can multiply them, you can just do whatever mathematical calculation you want to do with your rasters. Then again, I'm getting rid of the missing values. Just one thing to be careful with, if you're doing mathematical calculation between rasters, you're doing math. So if, for example, you end up with division by 0, that's a problem. So this is a problem, for example, you may end up with in your exercise. So if you're dividing and you're dividing something by 0, because you might have a pixel value that is 0. You're working with elevation of places. What if the elevation of 1 pixel is 0? Then you will get an error that, okay, there's a problem. So you should handle those cases carefully.